During this part of the lesson, I wanted to talk about nerve impulses. So here I have in front of me a picture of the cell membrane of an axon. And you can see here we have the intercellular side of the axon and the extracellular side of the axon. So interestingly enough, I want to talk a little bit about the cytoplasm and the extracellular fluid. There is a law called the Law of Electrical Neutrality, and that basically says that any aqueous solution, any solution of water with dissolved electrolytes is always electrically neutral. And that is the law of electrical neutrality. So that means there is always, if you add up all the anions and all the anions and all the cations, the charges will always net out to zero. And that is for the solution on the inside and on the outside. So, how is there a charge difference? Well, there is a charge difference very, very locally, only right along the inside and the outside of the cell membrane. Okay, so this difference in charge is only something that is happening right on, just several layers of molecules just along the inside and the outside of the cell membrane. Okay, and interestingly enough, this has been measured. If they get a really tiny electrode and they measure it, we know that when you measure this through a meter, we know that the difference of membrane potential is approximately negative 90 millivolts from the outside to the inside of the cell membrane. And this varies from nerve to nerve in different parts of the body, and it also varies from moment to moment as different things are occurring in the body, and I'll talk about that a little bit further on in the course. But the negative 90 millivolts is approximately what the difference is from the inside to the outside of the membrane, the difference in charge. Now, how does that difference occur? Well, we talked about, it all sort of begins with the sodium-potassium pump that we talked about in the previous lecture. So here I'm going to draw a picture of the sodium-potassium pump. And remember, this is the sodium-potassium ATPase pump because it requires the input of energy to work, because it is pumping ions against their concentration gradients. And what it does is it is constantly pumping 3 sodium ions outside of the cell and 2 potassium ions inside of the cell. So it's trading 3 sodium ions for 2 potassium ions. Now, this again is against the concentration gradient, because the concentration, for instance, the concentration of potassium outside of the cell is between 3.5 and 4 milliequivalents, and on the inside of the cell it's more like 140 milliequivalents. So this is a 35 to 1 concentration gradient. Okay, there's much more potassium inside the cell than there is on the outside. And sodium, it's kind of the opposite. The concentration gradient is not quite as much, but it is there. So with 3 positive ions being moved out of the cell and only 2 positive ions moving into the cell, this creates a slight charge difference, right? There are more positive ions starting to accrue just on the outside of the cell membrane than there are on the inside of the membrane. Now remember, the anions aren't changing place at all. This is only occurring with cations, the sodium-potassium cations. So just the sodium and potassium pump accounts for some of this charge difference. The other part occurs because there is another protein membrane, but there is another membrane protein called the slow leak potassium pores, and this allows potassium to leak out of the cell. And this constant leakage, so constantly potassium is being pumped into the cell, but at the same time it is slowly leaking out. And since more potassium is moving out of the cell than is moving into the cell, then this contributes even more to the increased positive charge on the outside of the cell and the increased negative charge on the inside of the cell. So that is how the situation occurs. Now, this difference in charge is known as the resting potential. And it's called the resting potential because this is the normal state of affairs at on the cell membrane of a nerve cell. And it is the opposite of an action potential. Now, interestingly enough, it's called a resting potential, but it's not something that just occurs at rest. It's something that requires a lot of energy. Remember, there's a lot of ATP going into the pumping of cations into and out of the cell. So this resting potential requires a lot of energy. But it is, again, the normal state of affairs to have the positive on the outside and the negative on the inside with a voltage difference of negative 90 milliequivalents. Now, why is this important? Well, the nerves in our body use the resting potential and action, and the difference between the resting potential and the action potential to send information from one area to another in the body. And so the next part we're going to talk about is the action potential. Now, okay, so action potential. All right, so let's draw the membrane again. And what we have here, we've got a positive charge on the outside and a negative charge on the inside with a difference of 90 millivolts. Okay, so what occurs now, once we have this resting potential that's maintained by the sodium-potassium pump and the slow leak of potassium, we have this resting potential, and what happens is there is gates. Now this is a voltage-gated sodium channel. Now, this gate can be triggered by two different things. There are two different types of gated sodium channels. There is the voltage-gated sodium channel, and there is a ligand-gated sodium channel. I'm going to talk first about the voltage-gated sodium channel. So what happens with the voltage-gated sodium channel is it opens up if it senses a change in the membrane potential. If the outside of the membrane becomes more negative, so if this negative 90 millivolts drops to, say, negative 60 millivolts, this change will trigger the gate to open up, swing into an open position. And when it swings into an open position, sodium can rush in. And lots of sodium rushes in, enough to change the polarity, because remember, sodium are positive charges, so we have all these positive ions rushing in, and this changes the polarity of the membrane. And what happens is this change in polarity will trigger the next sodium gate to open up. And then more sodium will rush in. And this will continue on. This will continue on down the line. And this is how information, this is called the propagation of the action potential. Okay, So the information is being passed on from sodium gate to sodium gate on down the um, on down the cell membrane, on down the axon. Okay. Okay, so I have here again the cell membrane, and you can see this is these are little phospholipids, and um, and on the outside of the cell, this is the extracellular side here, and the other side is the intracellular. The extracellular side is positively charged, and the intracellular side is negatively charged. Okay, and here we have several sodium gates. So we have lots of sodium out here. Remember, there's more sodium on the outside of the cell than there is on the inside of the cell, between 135 and 145 milliequivalents to be precise. So there's lots of sodium out here that's just waiting to be to get into the cell, to move down its concentration gradient from one side of the cell to the other. So only a couple sodiums over here. Okay, so what I have here is down at the bottom, I have what is called a ligand-gated sodium channel. Now, the ligand-gated sodium channel is the kind of gate that you're going to see at a synapse. And it is a gate. A ligand is a chemical that that can reversibly bind with another chemical. So in this case, this ligand is going to be a neurotransmitter. So a ligand-gated sodium channel is the kind of sodium channel that you're going to see on a postsynaptic membrane that's going to bind with a neurotransmitter and open up the sodium channel to start the propagation of a new action potential. Okay, so let's say we've got a little neurotransmitter here floating around, and it makes its way over to the ligand-gated sodium channel, and it binds with it. Now, when it binds with the ligand-gated sodium channel, the sodium channel is going to open up. And when it opens up, this allows lots and lots of sodium to rush in. Okay? So the sodium rushes in. Now when the sodium rushes in, it changes the polarity of the membrane. So this negative side here becomes the positive side, and the positive side becomes negative. Okay? Now, the book goes into details of, it gives you a little chart that shows you, the negative 90 millivoltage resting potential, and it probably goes up to a positive 10. And the voltage-gated sodium channel will have a threshold of maybe minus 60. So this is the threshold that the voltage-gated sodium channel will open up, and then more sodium will rush in, and the polarity of the membrane the charge of the membrane will change from negative 90 to positive 10, and then it will come back down again later on. And it comes back down again because of other channels, and we'll talk about that in a few minutes. Right now we're just focused on this first part of the action potential. Okay, so what's happening here is the sodium is rushing in, lots and lots of sodium is rushing in through this ligand-gated sodium channel, and this is changing the polarity of the membrane. And this next sodium channel is a voltage-gated sodium channel, and it notices the change from negative 90. Actually, it notices it on the inside from negative 90 to positive 10. And when it senses that change in polarity, it changes the shape of the gate, changes the conformation of the gate, so it is no longer closed, and now it is an open pore, and the open pore allows sodium to enter. Okay, and again, this continues on down the line. These change into positives, these change into negatives. This opens up, this triggers the next sodium gate to open up, which allows more sodium to enter. More sodium enters. The polarity changes here from then this allows the next gate to open, and more sodium enters. And this continues on down the line. And hence the propagation of the action potential moves from one side to the next. Okay, so how does the action potential end? Well, there are, in addition to there being voltage-gated sodium channels, there are also voltage-gated potassium channels, and the potassium channels open up as they detect the polarity change as well, and this allows potassium to leak quickly from one side to the other. So from the intracellular space to the extracellular space, and this is what causes the negative 90 millivolts to be quickly reestablished because of potassium, the fast potassium channels that get opened up by the change in voltage. Okay, so let me know if you have any other questions about that. The book does cover it in detail. I'm just hoping that I gave you enough of a background that that you will be able to understand how Goiten talks about the resting potential and the action potential. Now, Goiten goes into a lot of detail about the Nernst potential, the Nernst equation, and you do not need to know all the details of that. Just know that the resting potential of negative 90 milliequivalents is caused primarily by the unequal slow leak of potassium out of the cell with very little sodium leaking into the cell, and the constant pumping action of the sodium-potassium ATPase pump. Okay, beyond that, you do not need to know anything else about the Nernst equation.